Forces of nature, when they hit, can bring devastation.
Not sure if you can work some magic up at the control room.
Just went off in Simla.
And death.
Dozens of children were inside this building. Some have been found dead, and many are still unaccounted for.
For scientists, predicting these events is a big challenge. Even using the latest high-tech weather observations, there's still plenty of uncertainty.
Check, keep wandering.
But researchers at the University of Colorado Boulder are trying to close the gap, using aerospace technology to get them closer to the storm. The latest tool in CU's Grand Challenge, coming up on CU Science Update.
Copy that.
Soaring. The future of science breaks the chains of gravity. This aircraft flies under the control of a pilot
That's way out of there.
who remains earthbound.
I did this for fun from my early teens, and I would go out to the model airfield and fly planes and helicopters and all that, and that's what I did on the weekends.
And it's going to go a little bit further north than you are right now, but not by much.
Because that's the way the storm is tracked.
James Mack is a systems engineer and pilot for RECOV, CU's Research and Engineering Center for Unmanned Vehicles. Operated by faculty and students from the College of Engineering and Applied Science, their goal? To develop unmanned aerial systems for scientific experiments. Today, James is flying an aircraft that is distinctly yellow and appropriately named Tempest, which is undergoing flight tests at the Table Mountain National Radio Quiet Zone, 7 miles north of Boulder. Weighing 10 pounds and with a wingspan just over 3 meters, Tempest is about to experience a lot of turbulence.
You're looking pretty good.
So we do a lot of sampling of storms. So we do a lot of storm research and trying to figure out how they form and how to better understand them. And so these storms have a lot of energy, wind energy, etc., built up in them in order to form the storm.
Next pass, I'll go further north, not this one.
Tempest is being prepared for one of its toughest jobs: to fly into the unpredictable environment of a supercell thunderstorm.
Everything I do, almost everything I do, has not been done before. You know, we're blazing trail on every front, and so it's really exciting to be able to come into work and know that you'll be doing something that hasn't been done before.
Mac joined RECOV in 2012. He controls Tempest during takeoffs and landings.
That'll end 3, 2, 1.
And carefully monitors the aircraft once airborne.
If things are going really well, things are really boring for a while. So we'll sit back in our chairs and just kind of watch the aircraft flying around doing its thing. And then we wait until either the mission's complete or we run out of batteries, and then we set up for a landing and bring it in. Our landings are generally just in a grassy field somewhere.
Back at CU, Mac's workshop is loaded with drones used over the years. Small, just under 50 pounds, inexpensive, and they can be used in remote locations, without the need for runways. For years, RECOV has been deploying drones, for monitoring seal populations in the Arctic, changes in sea ice near Greenland, and even chasing tornadic storms. As a growing industry, drones are fast becoming popular tools for science, gathering data without the risk to life or limb in places otherwise inaccessible to people.
In terms of the term drone, we do fully embrace that now.
Brian Agro is a professor of aerospace engineering at CU and a co-founder of RECOV.
What people refer to as drones has changed. If you think about, if you had asked that question 5 years ago, what is a drone? The public, what would come to mind would be military machines. Now you say drone, and what comes to mind is a little quadrotor, and even toys.
The Recov drones are definitely not toys.
We make them smarter, faster, more efficient, all the technologies that go into that tool.
Eric Frew is an associate professor of engineering, co-founder and director of Recov. He attributes the popularity of drones to innovations in aerospace technology.
A lot of the underlying technologies in terms of the embedded systems, the computers, the electronics, those all have a heritage in the aerospace world.
Recov has more experience flying science missions than any other research group in the world. And the centerpiece of that research is Tempest. But for safety reasons, the Federal Aviation Administration won't permit it to fly in the National Airspace System without a certificate of authorization. For Argro and his team, the FAA granted Tempest a certificate, allowing them access only to certain areas and altitudes.
We typically will fly at 1,000 feet and above, well, hopefully above. We are currently getting FAA permission to fly up to 2,500 feet above the ground.
Under those rules, we're required to have certifications. The pilot in command is generally required to have a manned pilot's license. The unmanned aircraft, you're generally flying kind of from the seat of your pants. You don't have a lot of instruments available to you that you're flying from, at least with the small aircraft that we fly.
Tempest itself is designed to fly wherever the team sets up.
Yeah.
And once the FAA gives its approval, the typical deployment consists of a method that is familiar to many kids and their paper airplanes.
Our launcher is typically a big rubber band.
Pounding stakes in the ground, the team hooks up a winch that will catapult Tempest into the air. Wind direction is crucial. Tempest must be launched into the wind to ensure maximum lift. If the wind changes direction, the stakes get pulled up and relocated. In the meantime, Tempest is fitted with sensors, its guts exposed, while the navigation systems are checked and double-checked.
We have a pilot who's at the sticks doing the manual piloting, making sure the aircraft flies okay. We have an operator who operates the payload and makes sure that the aircraft is collecting the data it should, that all the onboard systems are working properly. And we have an observer who's there to make sure that the aircraft stays clear of other air traffic, people on the ground, things like that.
Without wheels, Tempest must essentially be carried and then held until the winch starts to pull. One mistimed release could spell disaster. No pressure.
Ready? 3, 2, 1. And it shoots off kind of like a slingshot. The operator will confirm that everything's working right. The pilot confirms that the aircraft feels right and that things seem to be working okay. If it all checks out, then we'll hand the aircraft over to the autopilot and let it do its mission.
Flying in the name of science, Tempest is unlocking the human potential to explore the natural wonders of the world. Tempest also leads the way in CU's Grand Challenge to come up with new scientific and engineering capabilities that will explore the world's most pressing problems.
So the CU Grand Challenge, Our Space, Our Future, is about leveraging the aerospace technology expertise on campus and combining it with the earth science expertise and space exploration expertise.
In collaboration with industry and government, CU will use its expertise in a coordinated effort to address changes in the environment, in resources, and climate.
I view this as a complete team effort. It takes the engineers working with the scientists, with the policy people, and then for us to discuss how relevant what we're doing is and how acceptable it is to the public. I mean, because there are the issues of taking data in new ways.
Recov will use its drone technology and the Integrated Remote and In-Situ Sensing Initiative, called IRIS, which will be coupled with a second initiative called EarthLab. which will be a state-of-the-art computing facility where researchers and students can use the real-time data to quickly generate new forecasts for the environmental risks from fires, floods, and droughts.
RECOV helps develop the new technology. Earth Lab and the earth scientists on campus will use the data that we collect to do the science.
IRIS is about ingesting and creating new sorts of data from new platforms, including drone technology. And Earth Lab is about ingesting large amounts of data and trying to integrate them and create new insights.
One of the initial projects will study droughts, which will merge satellite data with drone technology.
And what we want to do is figure out how we can create better information about droughts to help land managers make decisions about how they're utilizing their land in the context and in the face of drought.
Specifically, we're going to be looking at ranchers and drought. There are a lot of tools out there that decision makers use. There's in any sort of field, but within ranching there's drought tools, there's to try and determine whether you should cull your herd, is usually what you would do in the case of a drought, or purchase feed, truck them to a different location, and so kind of working to incorporate some of the new data into those tools.
Coupled with satellite observations, Tempest will collect data on soil moisture content to improve drought prediction and water conservation. Andy Lawrence is a fourth-generation rancher in northeastern Colorado. He's seen his share of dry spells.
The droughts in between 2002 and now, we had one about every 2 years literally there for a little while where we didn't get much moisture.
Some of these droughts can be devastating.
It was pretty sad looking. And of course we were moving our cows around constantly trying to keep from damaging the sod any worse. You know, we're feeding and then moving them to different pastures too, just kind of trying to get around. And it worked, but not as good as you'd liked it to work.
The grazing area is going to be really sensitive to drought. So if they're not reducing their herd, they're going to impact the ecology of where they're grazing. And that can have long-term effects that reduce the available forage for years to come.
And of course, then it puts you behind the 8 ball. You're trying to build your herd back up, and your income's not very much because you don't have very many calves to sell. So you're not able to keep a lot of replacement heifers to build your herd. So it takes a long time to build your herd back up. In fact, we're just now getting back to our numbers where we started the 2002 drought. We're just getting back to them here in the last couple of years now.
The hardest part about drought is the unpredictability.
Well, if I knew in advance that we were having a drought, we could make plans to maybe find grass some other territory, you know, go take our cows to the mountains or to Wyoming or Nebraska or someplace where there is moisture. But it's something you have to make plans ahead, because there's a lot of people in the same predicament that we would be in that would be looking for that. And the same thing happened in 2002. We were, this whole country was drought. Nobody had any place to go. And if there was any place to go, that was immediately grabbed up before, you had a chance to get there. So if we could know, which I don't know whether you'd ever be able to get that, but if you could know 6 months in advance what the weather was going to be like as far as, a drought or something like that, you could make future plans that probably could hold your place together a lot better than what we did in particular the 2002 drought, where we ended up having to sell a bunch of our cows.
And I think it comes down to better information and also the delivery of that information. So one piece that Earth Lab is going to create is a new visualization studio. So a place where people can actually come and look at these large amounts of data and help understand and interpret them. So on a day-to-day, you can imagine a rancher or farmer actually getting an ingest of precision data from a drone about the status of their fields and whether or not they need to irrigate, or whether or not they need to shift their cattle to another area, or whether or not they need to think about their insurance premium, and whether or not an insurance payout is coming in response to new information about drought.
And not only drought. One of the pressing problems for people living on the plains is the threat of tornadoes. Growing up in Oklahoma, Brian Argro is well acquainted with this threat.
In 1969, I was 8 years old, and there was a tornado warning. There was a storm that was hitting Prague, Oklahoma, that's about 20 miles south of my hometown of Stroud, Oklahoma. We had a storm cellar out back of the house. My dad was really proud of it. We could see that something was going on to the southwest of where we live, which was near Prague. And so then the sirens went off, and we went to the cellar. And so we were there, and the wind was blowing like crazy. It was raining. And then it got quiet. So my dad opens the door, and we look around, and it seems that, hey, this is over. So we go back in the house, and that's when the softball-sized hail started falling. And we couldn't get out of the house, and so we had to get under the beds. Now we have a storm cellar behind the house, and we end up having to ride out a local tornado. It didn't, hit right where we lived, but if it had, we would have been in the house. We couldn't get out because the hail was so large, it would have probably killed us, trying to get from the house to the cellar.
The experience galvanized his interest in storms. When he came to CU in 1994, Argro started looking into drones. Tempest was introduced in 2009 in the Vortex 2 project, the largest project of its kind to study tornadoes. In 2010, Tempest became the first unmanned aerial system to intercept a supercell thunderstorm, the kind that produces tornadoes. Now, in collaboration with EarthLab, Project Iris and Tempest embarks on a long-term goal to significantly increase tornado warning time and accuracy.
Right now, the average warning time for tornado warnings is about 14 minutes.
Mike Nelson is the chief meteorologist at 7 News in Denver.
Good evening, everybody. Plenty of cold air and a little bit of snow across the country today as we look at our surface map.
His career as a weather forecaster spans 40 years.
And we can expect just scattered thunderstorms throughout the day.
He's seen firsthand the deadly aftermath of tornadoes and is struck with finding better ways to warn people.
And you can now get watches and warnings right to your home phone. Go to Storm Shield Alerts.
And so if we can get 30 seconds, 60 seconds, a few minutes of additional time out to the public to warn them on an impending storm that may produce a damaging tornado or large hail, that's going to be very important.
This storm, we're going to keep a close watch on. It's had some signs of rotation. That's why we're a tornado warning on it. And of course, you heard
Nelson keeps up with the latest advancements in radar, satellites, and supercomputers to lengthen the warning times of severe storms.
What we can now do out to about 5 days is what we used to be able to be good at to about 2 days. So we're getting much, much better at the ability to foresee a dangerous storm system over a period of days. Now, we need to bring that technology down a level of magnitude so that we can be better on forecasting local severe storms instead of a few minutes in advance, perhaps 30 minutes, 60 minutes, a couple of hours in advance. This is the kind of thing the new technology is going to help us do.
It's all about observations.
Jim Wilson is a scientist at the University Corporation for Atmospheric Research in Boulder. He's interested in using unmanned aerial systems to nowcast severe storms, short-term forecasting that uses real-time data to identify hazardous weather more accurately, while dramatically improving warning times and advisories. And to make nowcasting work requires lots and lots of observations that are close in time and space.
And of course, that's one of the big difficulties, is that we don't really have observations that close in time and space. Just a very few places would have that sort of observation density.
The best forecasting tools available use radar and satellites, but they don't give information about temperature, moisture, and winds with enough detail.
And that's what we really need if you're going to be able to forecast or nowcast where a storm's going to be specifically in 30 minutes or an hour.
The technology we have now, what we're developing, will allow us to look at those real fine scale, the micro scale mechanisms inside of a severe thunderstorm. What's the difference between this one that doesn't drop a tornado and that one which looks to the eye and on the radar to be the exact same storm, but it does produce a damaging tornado.
Enabled by aerospace technology, drones can fly into supercells, thunderstorms that contain persistently rotating updrafts called mesocyclones. A structure that inspired Nelson's famous presentation to school children, the tornado dance.
So the air rises up through the thunderstorm like smoke through a chimney. The big thunderstorm builds high in the sky. The jet stream comes by to make the whole thing spin. It starts out spinning kind of slow, but then just like the figure skater, it gets smaller and faster and faster and smaller, and the tornado forms way up in the heart of that storm and then works its way down through the thunderstorm down to the ground.
Watching it. We know it's west of here. We know it's east of all.
So we're here a little south of the Pawnee National Grassland in northern Colorado, and our objectives are to find some thunderstorm outflows and maybe even some heavy rain cores and thunderstorms.
Conrad Ziegler, a meteorologist with the National Severe Storms Laboratory, collaborated with CU on test runs for Tempest. He hopes to use Tempest to examine storms up close, to collect data on the outflow dynamics of supercells, including the development of rear flank downdrafts, an area of quickly descending air thought to be connected to the formation of tornadoes.
For years, we have had measurements from probes like the Mesonet behind me that are giving us conditions a few feet off the ground, but what we really have lacked is to have more comprehensive measurements of the temperature, humidity, and winds in the layers above the surface.
Okay, positive pitch.
Ground-based radar can get some information about winds.
Positive yaw.
But Tempest can take measurements higher.
So the Tempest aircraft is absolutely vital for that. We have, besides radars, we have no other way of measuring the conditions directly inside of that outflow.
Weather balloons record similar measurements.
All right, okay. Ready?
We're going.
But the problem with weather balloons is that they go where the winds take them. Tempest won't have that problem, and it will soon get its chance to prove it. The forecast for today calls for thunderstorms in northeast Colorado, which includes the Pawnee National Grassland. The warm and humid atmosphere is perfect for the formation of supercells, prompting the Recov team to set up shop just south of the grasslands to watch and wait. Further south near Denver, the storms are building, moving northeasterly. Chances are good that Tempest will get to intercept the storm.
77 and 86. 392.
But the team needs to make sure it flies within the boundaries set by the FAA. Ziegler hopes Tempest can take measurements specifically from a pocket of cold air that forms near the ground under a supercell.
So typically very cold air lies down at the ground, but there are questions such as how cold is the air aloft? Is there a large temperature gradient between the surface and the flight level of the aircraft? Is the cold air uniformly deep, or does it have an inversion, as it were, with very cold air near the ground and warmer air aloft?
Tempest's job will be to fly through the outflow and take measurements as the air descends to the ground, using new sensing devices.
For the first time in this experiment, we have a new device that measures very fine details of changing air currents relative to the moving aircraft. So this gives us very, very precise measurements of the local wind relative to the aircraft.
During our interview, reports come in of a tornado on the ground near Denver International Airport, about 30 miles to the south.
Could I ask him about if he knows about that? Yeah. So you know about the tornado on the ground?
Yeah, we need to wrap this up.
Yeah. Okay. Yeah, I think he's saying we're probably getting ready to go here, so.
Okay. Attention, please. The National Weather Service has issued a tornado warning that includes Denver International Airport concourses and terminal. Take shelter immediately in marked.
Videos taken by airport passengers capture an eerie, swirling cloud, a sight that prompted evacuations and diverted flights.
Stay away from windows and be alert for further instructions.
Further north, the team arrives on the outskirts of the Pawnee grasslands. but they're still too far from the storm to see anything significant. Yet even from this distance, the outflow can be felt. Time to deploy Tempest. Tempest makes wide, sweeping orbits.
Okay, move the waypoint north.
We have the luxury of working with collaborators, particularly from the University of Nebraska, who know a lot about these storms, how they evolve, how they move, to put us in the right place at the right time.
Copy that, moving waypoint north, and please advise that you have...
Although the storm kept well to the south, Tempest manages to send data on wind, pressure, temperature, and humidity back to the control van. Enough data to keep the scientists busy for months. After a 30-minute flight, Tempest makes a grassy landing. Doctoral student Roger Lawrence III joined Recov to get hands-on experience with unmanned aerial systems.
I grew up in Miami, and I was always interested in hurricanes. And for the longest time, I wanted to become a hurricane forecaster. And then came here for aerospace engineering. And once I found out that it was for weather research, I was ecstatic. You know, I've always loved severe weather. It's always made me excited. You know, it is nice working on, one, something I really like, but something that also will help out other people.
Lawrence wants to find ways to make drones economical, but not cheap.
This way, if we crash and break something, you know, we aren't spending thousands and thousands of dollars to fix it.
The faculty and students working on projects IRIS and Earth Lab will get real-world opportunities to meet engineering challenges.
I'm an engineer, and so we generally look for solving technical problems, but technical problems aren't always the biggest problem or the reason for doing something. So it's good to engage people who have ideas of how these can be used and better ways to use them in that discussion.
Aerospace technology that allows us to get into space can also be brought down to Earth. In late 2015, CU engineering students displayed their innovations in interactive exhibits known as space pods, seen as part of the Grand Challenge kickoff in Denver's Museum of Nature and Science. Virtual reality,
I can see everyone using augmented reality on a daily basis.
Asteroid mining, wearable technology.
How do we basically teach our clothing to recognize whether or not I feel hot and cold?
These space pods build on a rich 50-year history of CU's strengths in aerospace-enabled science and technology, which also caught the eye of a prominent science enthusiast who happened to be the keynote speaker at the Grand Challenge kickoff.
If I were king of the forest, we would invest in university space programs so that we bring a lot of people into aerospace and solve these great big problems. We're going to need renewable sources of energy. And the most likely one, especially here in Colorado, is wind and solar. Research into those two things will affect spaceflight. And everybody's wondering about climate change. What are we going to do with these fires? How are we going to get fresh water or clean water to people over the world? To research that, you need spacecraft. You need assets in space. So it's all, to me, it's all one thing. Investing in basic research pays back many times over.
Among those investments, finding new innovations to get Tempest airborne.
All right, take 2 of the controlled aircraft.
James Mack and his team recently tested a prototype for a pneumatic launcher.
The breadth of what you have to know to do this well is so enormous that it's really great to be in a job where you're exposed to all that and where you can be engaged in that whole process. So there's so much learning to do. There's so many things to be good at when I come to work each day.
you.